You know, for centuries, certain math problems have been the ultimate test for the human mind. But imagine if, for 200 years, one of the biggest problems was just declared impossible. The greatest minds agreed it couldn't be solved. But what if they were all wrong?
Yeah, we're talking about a very specific beast, high-degree polynomial equations. For generations, mathematicians, some of the smartest people on the planet, would get to this point and just hit a brick wall, and the conclusion was unanimous. This is unsolvable. A permanently closed door in the world of algebra.
And this wasn't just a hunch. In 1824, a mathematician named Niels Henrik Abel formally proved it. He established a theorem that basically said there is no general, exact solution for these really complex equations. It became a fundamental law, a line in the sand to define the very edge of what math could do.
So, what if that unbreakable wall, that fundamental law, was just a big historical misunderstanding? What if the impossible was never really impossible to begin with?
Okay, to really get how big of a deal this is, we have to appreciate the sheer weight of this 200-year-old problem. This wasn't some obscure little puzzle. This was considered settled science.
Let's just look at the timeline here. Way back in the 1500s, mathematicians were on a roll. They cracked third and fourth degree equations, but then, for almost 300 years, nothing. Progress just stopped. Then, in 1824, Abel's theorem goes up, and it's like a giant do not enter sign. A few years later, the brilliant Galois comes along and uses this brand new thing called group theory to explain the deep structural reason why that wall was there. And for nearly 2 whole centuries, that was the end of the story. Until now.
So this is the official law, the Abel-Ruffini theorem. And the key phrase to zero in on is solution in radicals. Now, what does that mean? Well, think of it like this. You can't find the exact answer using your standard mathematical toolkit. You know, adding, subtracting, multiplying, dividing, and taking roots. The tools just weren't powerful enough.
And this led to this kind of mathematical fatalism. It's like, why would you even bother searching for an exact answer that's been proven not to exist? So instead, we started leaning on computers to just give us close enough approximations. For all intents and purposes, the case was closed.
But you know how it is. Some people just don't accept that a boundary is final. And that brings us to the challenger, who believes he found a crack in that very, very old wall.
This is Professor Morad Sultan Ezouidi, and he looked at this 200-year-old impossibility and saw something completely different. He didn't see an end. He saw the beginning of a much deeper truth.
I mean, this quote from his work really captures the entire spirit of this breakthrough. He's basically arguing that Abel's theorem was never the final word. It was just a historical milestone, one that was just waiting for someone to come along and surpass it.
So what is he actually claiming here? Well, first, that he's found a complete and totally exact symbolic solution for a 7th-degree polynomial. But here's the crucial part. He isn't saying Abel was wrong. No, he's saying Abel's framework, the very lens he was looking through, was incomplete. Ezouidi's work isn't about breaking the rules. It's about expanding the playing field itself.
So how on earth do you solve the unsolvable? Well, you have to invent new tools. You have to write new rules. You have to find a door that absolutely no one else even knew was there.
The classical approach gets completely tied up in its own complexity. It's like an impossible knot. What Ezouidi's approach does is it doesn't even try to untie the knot. It just finds a way to bypass it completely. It uses this new method of recursive transformations. You can almost picture it like a set of Russian nesting dolls. His method finds a clever way to open each doll, one by one, until it reveals the simple, elegant core hidden right inside. And the difference here is, well, it's a genuine paradigm shift. Where the old methods threw their hands up and said impossible, Ezouidi's theorem says, no, it's achievable. Where they had to settle for fuzzy computer approximations, this new method gives you 100% algebraic, verifiable accuracy. It's a total rejection of that old mathematical fatalism.
Okay, but theory is one thing. How does this actually work? Let's take a quick conceptual peek at the theorem in action, actually unlocking a solution.
So the heart of the idea is this thing called recursion. The method creates a chain of related algebraic identities, and with each step in the chain, it gets closer and closer to the answer. It's like it's using the equation's own DNA to solve itself.
Now, don't worry, we're not going to get lost in the formulas here. But just look at how logical the process is. You start in step 1 with your big, complicated polynomial. Then, the recursion kicks in. Steps 2, 3, and 4 start peeling back the first few layers. Then steps 5 through 7 just keep that process going, digging deeper and deeper. Each step is a rigorous, verifiable algebraic move, until finally, step 8 reveals the solution.
And after all that incredible recursive unpacking, for the specific example used in the proof, the final solution emerges. And it's just 0. Perfect, symbolic clarity. No approximation, no estimation. Just an exact, simple answer.
Now, this is so much more than just a clever trick for one equation. I mean, if this work holds up under peer review, this could signal a whole new era for algebra. A world without those old familiar walls.
Because, really, the implication here is absolutely profound.
This isn't just about finding x anymore. It challenges the entire philosophy of what to solve even means. It's a shift from a mindset of limitation to one of pure, unadulterated discovery.
And this, right here, is the ultimate statement from Professor Ezouidi's work. It's this incredible idea that every polynomial, no matter how ridiculously complex it is, already contains the complete blueprint of its own exact roots, that there's no limit. And that's what it leaves you wondering, right? For 200 years, this was seen as a fundamental limit of math. If this wall can actually fall, what other so-called impossible problems in science, in technology, are just sitting there waiting for someone to come along with a new perspective and find a door that no one else ever knew was there?